A grindstone. A 50 kilogram grindstone is a solid disc 0.52 meters in diameter. You press an axe down on the rim with a normal force of 160 newtons, as you can see in the figure. The coefficient of kinetic friction between the blade and the stone is 0.6, and there is a constant friction torque of 6.5 newtons meters between the axle of the stone and its bearings. Part A: how much force must be applied tangentially at the end of a crank handle 0.5 meters long to bring the stone from rest to 120 revolutions per minute in 9 seconds. Part B: after the grindstone attains an angular speed of 120 revolutions per minute, what tangential force at the end of the handle is needed to maintain a constant angular speed of 120 revolutions per minute? Part C: how much time does it take the grindstone to come from 120 revolutions per minute to rest if it is acted on by the axle friction alone? Okay, so first of all, our grindstone is a uniform solid disc, and we know the moment of inertia for rotations about the center of mass is mr square over 2. That's from problem 9.53. So if we substitute the values here, the mass of the grindstone is 50 kilograms. The radius is 0.52 divided by 2 meters squared divided by 2. So we obtain 1.69 kilograms meters square for the moment of inertia of the grindstone. And we have kinetic friction Fk, which is the coefficient of kinetic friction mu k times the normal force. We have a 160 Newton normal force and 0.6 kinetic coefficient, friction coefficient, that gives us 96 newtons of kinetic friction acting on the grindstone. Now let's take a look at what is happening here. We have the kinetic friction acting on the grindstone. So the grindstone is rotating in the counterclockwise sense here, and the kinetic friction will oppose this. We have the normal force being exerted that is basically causing this kinetic friction. We have a friction force that is on the axle, between the axle and the bearings of the grindstone, and we have a tangential force being applied at the end of this handle. So if we look at the torque being applied by this force F, the tangential force, it is R cross F. So R is the distance between the pivot and the application point of the force, so that is this distance d, 0.5 meters, which is equal to the length of this crank handle, 0.5 meters. So that's going to give us d times f. So if z-axis is pointing to the right like this, it's going to be r cross f. You point from the pivot point to the application point of the force, curl your fingers towards the force, you see that the torque is in k hat direction. So df k hat. And there is a friction torque applied by the friction between the axle and the bearings that is going to be opposing this torque exerted by the handle. So it's going to be minus 6.50 Newton meters k hat. That's opposing the rotation, opposing the motion. Now you can see that the sense of the rotation is basically omega vector pointing in plus k hat direction. So you curl your fingers in the direction of omega, you will see that your thumb points in plus k hat direction. So omega vector is omega in k hat direction. So therefore the friction torque must be in minus k hat direction. Now what about the torque exerted by kinetic friction? So if I go from the pivot to the application point of this kinetic friction force, the distance is r, and the perpendicular distance is r times fk. Now my right hand rule tells me that if I point from the pivot towards the application point of fk, curl my fingers towards fk, my thumb points in minus k hat direction. So this is basically the radius 0.52 meters divided by 2 multiplied by kinetic friction 96 newtons in minus k hat direction. So I find that this torque is equal to minus 24.96 newtons meters in k hat. So it's in minus k hat direction. So my job is now to calculate the net torque acting on it. The net torque, tau net, will be equal to, the first one is 0.5 f k hat, so 0.5 f k hat. The second one is 6.5 in minus k hat, and the third one is 24.96 in minus k hat. So this gives us 0.5 f minus 31.46 newtons meters in k hat. Okay, so I have found the net torque acting on it. Now in part A of the problem, how much force F must be applied tangentially to bring the stone from rest to 120 revolutions per minute in 9 seconds. Okay, so the net torque, according to Newton's second law rotational form, is equal to the moment of inertia times the angular acceleration alpha. So the angular acceleration alpha will be equal to the net torque divided by I center of mass for the uniform disk that I have calculated. Now the net torque was 0.5 f minus 31.46. So this will be divided by I center of mass 1.69 kilograms meter square in k hat direction. So this is my alpha vector. Now the final frequency of the rotation will be 120 revolutions per minute. That is 120 revolutions per 60 seconds, and that gives me 2 hertz of frequency. So the angular frequency will be 2 pi f, which will be equal to 4 pi radians per second. That's the final angular speed I'm looking for. Now the angular acceleration alpha, because I'm going to have a constant angular acceleration, it will be delta omega divided by delta t equal to the average angular acceleration, and I'm looking for a change in omega from 0 to 4 pi radians per second, 4 pi minus 0 in 9 seconds. So that is 4 pi divided by 9 radians per second square. Therefore, I find that 0.5 f minus 31.46 divided by 1.69 kilograms meters square must be equal to 4 pi over 9. And if I solve this for F, I will find that F must be equal to 67.6 newtons. Now part B. Part B says, after the grindstone attains this angular speed, what tangential force is needed to maintain this constant angular speed? Okay. Now I'm going to have alpha is equal to 0 radians per second square, so that the net torque acting on the grindstone should be 0 newtons meters k hat. Well, this will be satisfied if 0.5 F minus 31.46 is 0. That means the force will be equal to 31.46 times 2, which is 62.9 newtons. So 67.6 newtons is needed to bring it to 120 revolutions per minute, and 62.9 newtons is needed to keep it there. Now part C is asking, how much time does it take the grindstone to come from 120 revolutions per minute to rest if it is acted on by the axial friction alone? Now the force is 0. The force is 0 newtons, and we have no kinetic friction. We're not applying a normal force. Then we have only the net torque is equal to minus 6.5 k hat, which must be equal to I center of mass times alpha. So this will give us for alpha minus 6.5 divided by 1.69 k hat, which is the change in the angular speed delta omega divided by delta t. So our final angular speed will be 0 radians per second. Initial angular speed was 4 pi radians per second, and therefore the delta t that we will find is 1.69 times 4 pi divided by 6.5, which is equal to 3.27 seconds. Okay, so to summarize, in this problem we have a grindstone, 50 kilogram grindstone. It's a solid disc. First thing I did was to find its moment of inertia for rotations about the center of mass, which was calculated to be mr squared over 2 in problem 9.53. So here I have 50 kilograms, 0.52 over 2 meters as its radius, and divided by 2, I obtain the moment of inertia. You press an X down on the rim with a normal force of 160 newtons, and the coefficient of kinetic friction between the blade and the stone is 0.6. So 0.6 times 160 will be counteracting this rotation. So we will have this kinetic friction that is opposing this rotation here. And there's a constant friction torque, 6.5 newtons meters, between the axle of the stone and its bearings. So between the axle and the bearings we have another friction, and this friction will be also in the same direction, applying a torque in the same direction as Fk. So this friction and this friction are both applying a torque in minus k hat direction. That is basically trying to stop this rotation in the counterclockwise direction. So we want to apply a force tangentially at the end of a crank handle 2.5 meters long to bring the stone from rest to 120 revolutions per minute in 9 seconds. So we apply a force here. This is the blue force, not the normal force that we're applying here. That's going to cause R cross F is in plus k hat direction for this force. You can see that R cross F is in plus k hat with the right hand rule. So that will accelerate that will cause angular acceleration to bring it from 0 angular speed to 120 revolutions per minute frequency in 9 seconds. So we calculated the torque components here. This F is applying a torque in a plus k hat direction. It is d times F in k hat direction. The torque applied by the two friction forces are both in minus k hat direction. This one applies a torque minus 6.5 newtons meters. Here the torque is given directly. This one applies a torque in minus k hat direction, perpendicular distance r times fk, so that gives us 24.96 newtons meters. The net torque is due to these three torque components. The net torque is equal to I alpha according to Newton's second law of rotational form, so we can pull alpha as a function of F from this equation. Given that we have a final frequency of 120 revolutions per minute, that's equivalent to 2 Hertz, final angular speed is 2 pi f, which is 4 pi radians per second. And with a constant angular acceleration, because all forces are constant here, we have alpha is equal to 4 pi over 9 radians per second, and this gives us a force F that is being applied tangentially on the crank handle, 67.6 newtons. In part B, we want to keep this angular speed, and we need to apply a force to keep this angular speed. So angular acceleration will be 0, and the net torque has to be 0. So this gives us a force 62.9 newtons needed to keep the angular speed constant. And in part C, now this tangential force is 0, and also the normal force is 0, therefore kinetic friction is 0. We only have the friction between the axle and the bearings remaining. So if it's acted on by the axle friction alone, that's the only friction. And that gives us a minus 6.5 k hat torque in minus k hat direction here. So alpha will be delta omega over delta t. Final angular speed will be 0, initial 4 pi radians per second. That's what we have found in part A. So that gives us delta t is equal to I delta omega over the torque applied by friction, 3.27 seconds.